Okay, so we can start. So welcome everybody. Today we have Zoe Holmes from the EPFL in Lausanne, and she's going to tell us about hybrid, variational, classical quantum computing and ingredients to make it work. So whenever you want, Zoe, thank you so much.
Oh, wait, I need to share my slides, don't I? Okay.
I think I need to allow you, yeah. Okay, now you should be able to share your slides.
Right, okay, yeah, so title of my talk, Hybrid Variational Quantum Computing, Ingredients to Make It Work. And please do interrupt me as I go along. So what do I mean by hybrid variational quantum computing? Well, this is a very broad term, but for the purpose of this talk, I'm going to focus on any method that optimizes a parameterized quantum circuit by minimizing a quantum cost function, potentially using training data. And so this encapsulates variational quantum algorithms and some, but not all, quantum machine learning methods. And as I'm sure most, but maybe not all of you are aware, this is a sort of very popular, flexible tool, both for basic science and with potential industrial applications. So there's been lots of interest in it. This review on the framework from only 2 years ago has, when I last checked, over 1,500 citations. And to some extent, rightly so, it's a very flexible paradigm. So originally, this paradigm was put forward for things like finding ground states for condensed matter and quantum chemistry problems. But since then, people have come up with applications in all sorts of areas, from sort of combinatorial optimization, compilation problems, dynamic simulation, and it's at the core of many of these sort of quantum machine learning algorithms. There are even these neat papers where it's trying to apply variational quantum algorithms to sort of foundational problems that I find quite fun. Okay, so, but despite the popularity of this area, it's generally hard to assess the scalability of these methods towards quantum advantage. Because one, we lack the large, reliable quantum computers. So we can't just run our algorithm on big devices and see that they work and do something useful. But by definition, classical simulations in the regime of quantum advantage are also by definition impossible. So we can't just sort of straightforwardly test these algorithms. So instead, if we want to try and understand their scalability, we're going to have to use analytics. And so that's sort of the basis for this talk. I'm going to pin down 3 different ingredients that are necessary to make this framework work. So the first is expressibility, roughly how likely it is that your parameterized circuit contains a solution. Second is trainability, which is roughly how easy it is to minimize the cost. And the third one is going to be generalisability. So that is roughly how good whatever solution you find actually is. And that's going to depend on both the amount and the quality of the training data you have. Okay, but before I get onto those ingredients, let me start by pinning down one example, which is sort of an illustrative example that I think is good to bear in mind for sort of pedagogical purposes as I pin down these ingredients. And it's also just an example that I quite like, and I think at some point I might come back to explaining why I quite like it. Okay, so the example I'm going to spell out is quantum process learning. So the idea here is you have some unknown quantum process and you want to go about learning it. So as a theorist, I'll confess I'm guilty of often thinking of this unknown quantum process just as some kind of black box that I can feed states into and I'll get some other states out. But if you're more experimentally minded, maybe think of it as maybe some funky laser pulse that you can apply to an atomic lattice, or think about it as some interesting optical material that you can shine some light through. Okay, and then the first thing you're going to do if you want to try and learn this process, or one thing you could do, is study the effect of that process on a given input state. So that is, you feed some input state into your unknown quantum process, and this gives you some output state. Then what you might try and do is try and learn to replicate that process on the same input state. So that is, you're going to come up with a guess process, feed your input state into it, and just keep on fiddling around with your guess until it gives the right output. Then, once you've done that for a given input state, you can try and play exactly the same game for another input state. Just fiddle around with your guess until it agrees and gives you the correct output, roughly, not just on that new input state, but also your original input state. Then you want to repeat this for a whole set of different input states, i.e. a training ensemble. And in the end, you'll have your sort of best guess of your quantum process, your learned quantum process. And the question is, how well can this learned process make predictions on unseen inputs? So that is, if you feed in a new input state that you've not seen the action of your process on before, if you feed it into your learned quantum process, that's going to give you a predicted output state. And the question is, how well does that predicted output state match your true output state? So that is, how well can we use the learned process to predict outputs on unseen inputs? Okay, so for the purpose of this talk, for this example, I'm going to focus on learning unitary processes. So the idea here is to find some parameterized unitary and optimum parameters alpha opt, such that your parameterized unitary with those optimum parameters is roughly equal to your target unitary. So by target unitary, I just mean the mathematical representation of the black box I had earlier. So the unitary matrix governing the dynamics of your closed quantum system for a given amount of time. And by parameterized unitary, this will typically, but not always, be a parameterized quantum circuit. So that is, you're going to have some kind of arrangement of gates, and they will be parameterized. Okay, so how does this game look like in this mathematical formalism? Well, the idea is now your unknown process is represented by some target unitary u. You can feed in some input state psi, and that's going to give you some output state psi out. And then what you want to do is have your guess process v of alpha, and you want to optimize alpha to minimize the distance between your true output and your guess output. So here I'm going to use the 1 norm squared. In theory, you could use different norms, but we'll see why the 1 norm squared is convenient in just a minute or two. And then what you want to do is repeat this for a whole set of training states. So that is your training ensemble, your state psi I for I equals 1 to n. And this is going to be equivalent to minimizing your training cost. So that is just going to be your average error over your training data. So the average distance between your true outputs and your guess outputs, averaged over all states in your training ensemble. You'll notice that we've got this factor of a quarter that's appearing. This doesn't do anything important. It just keeps this cost function normalized between 0 and 1, but otherwise it's arbitrary. Okay, so why do I use the 1 norm squared? I use the 1 norm squared because the 1 norm squared difference between two pure states is equivalent to an average fidelity, but it's equivalent to a fidelity. So that means this cost is equivalent to the average fidelity between your true outputs and your guess outputs, averaged over all states in your training ensemble. And an average fidelity is easy to measure on a number of platforms. So you just, I guess it's kind of sketched here, you just prepare your initial state, you evolve down to your target, you try and undo that evolution by applying your guess or your inverse of your guess, and then you do a projective measurement to see how well you got back the state you started with. And then you repeat this for all the states in your training ensemble. That's going to give you your cost. You're then going to minimize your cost using your favorite classical optimization algorithm, gradient descent, Bayesian optimizer, some SciPy black box optimizer that you don't really know how it works, to be honest, but it seems to do the trick. Run your favorite optimization algorithm. That's going to give you some optimum parameters alpha opt. And if all goes well, you should have that V of alpha opt is equal to roughly your target unitary. Okay, why do I like this example of learning a quantum process? First use I potentially see, and this is sort of a big dream I will accept, is the idea of trying to study unknown experimental quantum processes. So the way I usually like to motivate this is to highlight that, of course, classical computing power is currently routinely used to process data from quantum experiments. Classical computing power is also routinely used to control and manipulate quantum experiments. You don't just have a poor PhD student in the lab writing down every number that they get from the quantum computer and then, I don't know, doing long division to try and compute the results. But nature isn't classical, damn it. So if you want to experimentally probe and control and process it, maybe you'd be better off using a quantum computer. Sort of butcher the overquoted words of Feynman. So the thought here is that you could use something like quantum process learning to learn a digitalization of an analog quantum process. So in this case, you would be some unknown process, some funky laser pulse that you can apply to your atomic lattice. And V of alpha would be a parameterized quantum circuit. And what this would do is it'd give you a way of uploading your process to a quantum computer for further processing. So once you have a way of implementing your previously unknown quantum process on a quantum computer, You can then feed in states that maybe would have been hard to prepare experimentally, do measurements that might have been hard to do experimentally, apply that process multiple times in order to simulate longer evolution under that process. Sort of the world's your oyster, you've got a universal quantum computer. And if this seems a little bit abstract, I think the way to think about it, at least in the nearish term, would be to remember that a quantum computer can be thought of both as a quantum computer and as an interesting experimental quantum system. So thinking about measuring its fidelity from before, you could think about your experimental setup as a quantum computer in order to prepare initial state, and then switch perspective and think about it as an interesting experimental system to apply the analog process you want to characterize, and then switch back to thinking about it as a quantum computer in order to apply the inverse of your parameterized quantum circuit and then your final measurement. Okay, so that was the first possible use, experimental characterization. Second possible use would be compilation, either on a quantum computer or fully classically. So in this case, in contrast to the experimental characterization, your target unitary is known. And now your parameterized quantum circuit, or your parameterized unitary, is designed to replicate the known U in a particular way. So using particular structured form. The simplest would be just to compile, say, a short depth circuit to implement a particular algorithm you want to implement, i.e. maybe a short time evolution trotter step on a particular quantum computer, which has maybe necessarily limited gates and connectivity. Okay, so those are the two uses, characterizing an unknown experimental process and compilation. But the thing I want to highlight is I've run through this example because I like the example, and I think it's useful to bear in mind pedagogically for my talk. But of course, this framework is much more general. The core idea is you just need to pick your cost and your circuit such that if successfully trained, the optimal parameters, circuit and cost, are in some sense an approximate solution to whatever problem you're trying to solve. Okay, so back to my ingredients. First one I'm going to talk about is expressibility. And the thought here is that if you're going to try and make one of these algorithms run, one of the first things you're going to need to do is pick an ansatz for your parameterized quantum circuit, i.e. your guessed unitary. So you're going to need to decide how you're going to arrange your gates and how you're going to parameterize them. Then, given a possible input vector of parameters, so this is a bold alpha, so it's a vector of alpha 1, alpha 2, alpha 3, etc. For every corresponding input vector parameters, there's going to be a corresponding output unitary. So given a set of different input parameters that you can feed in, so this is a set of different input vectors. And note this will generally be a continuous set because generally each of these rotation angles will be allowed to vary continuously. So given this set, i.e. all the different possible basically angles you can feed in here, you'll have a corresponding set of accessible unitaries. So the set of unitaries which is produced by this ansatz. Okay, now to learn a target unitary in the context of quantum process learning, you're going to need a Gouks approximation of your target unitary to be captured by your ansatz. So that is, you're going to need to have V of alpha opt is equal to U of A for some alpha opt to have any chance of learning some target unitary UA. Or more generally, thinking beyond the quantum process learning example, you're going to need to have the set of approximate solutions to whatever your problem is, and the set of unitaries accessible by your ansatz to intersect. So you're going to need to have the unitaries accessible by your ansatz to contain some solutions. So this is sketched on the left here. So the green blob, the grey blob is meant to represent the total space of unitaries. The green blob and the red blob are meant to represent two different sets of solution unitaries to two different problems, problems A and problems B. And then this blue oval is meant to represent the set of accessible unitaries for a particular ansatz. So you can see that this ansatz contains solutions to problems A, but not problem B, so it could be used to solve problem A, but not problem B. Okay. Now, in the absence of prior knowledge about where your solution lies, or if you want to come up with an ansatz that's going to work for as many different problems as possible, your best bet is going to be to use an ansatz that explores the space of unitaries as fully and as uniformly as possible. So such ansätze are known as expressive ansätze. So the ansatz I showed you before is pretty inexpressive and correspondingly contains solutions to problem A, but not problem B. This new one on the right, however, is pretty expressive. It explores the space of unitaries pretty well, and then correspondingly contains solutions to both problems A and problem B. So in the absence of prior knowledge, your best bet would have been to try and use an ansatz that is expressive. But just because an ansatz contains a solution doesn't mean you can find it. It's like an Easter egg hunt. Just because you're looking in the right room doesn't mean you'll actually find any eggs. And that takes you on to the second ingredient. Second ingredient is trainability. So our cost landscape, as I'm sure any of you who have worked on VQAs is very aware of, needs to be sufficiently featured to enable training. And this is easiest to think about in terms of gradient descent, but the argument equally applies to non-gradient based optimization methods. Okay, so the problem here, and this is think about trying to train. If you have basically no gradients, like this sort of little man on the right here, you can have a damn hard time trying to train. You're just going to basically end up doing a random walk, and trying to find the lowest point on this field here is going to be hard. But if you have lots of gradients, training should be easier. And now this is particularly a problem in the context of trying to minimize a quantum cost. Because the problem is, if you have small gradients, then you're going to need very high precision measurements to find a cost minimizing direction. But if you need high precision measurements, this is very resource intensive on a quantum computer, because remember that on a quantum computer, a cost is only ever obtained statistically. So if you want a cost of precision sigma, you're going to need 1 over sigma squared shots. So if you want to determine the gradients to high precision, you're going to need lots and lots of shots. Okay, so in order to assess the trainability of landscape, what we do is we evoke Chebyshev's inequality and study the variance in the partial derivative of the cost. And it's recently been shown, well, actually now we're talking sort of 2-3 years ago now, that for a wide class of different ansätze, we have something called the bound plateau phenomenon. So the bound plateau phenomenon is when the variance in the partial derivative of the cost is shown to scale exponentially with the number of qubits that the problem acts on. So in the case of quantum process learning, it would be both, I guess, the size of the target unitary and the number of qubits the parameterized quantum circuit acts on. More generally, this n is the number of qubits your parameterized quantum circuit acts on. Okay, so it's been shown that the variance in the partial derivative of the cost scales exponentially in n. If you combine this with Chebyshev's inequality, what you get is that the probability of observing non-zero gradients vanishes exponentially with problem size. So for small-scale problems, the type that we can run via Qiskit easily on our laptops, we might see substantial gradients and we might be able to train. But as we get to larger and larger problems, the type of problems where we really might hope to achieve a quantum advantage, our landscape is going to become flatter and flatter and eventually be untrainable. Combined with the fact that if you have small gradients, you need many, many shots. What this implies is that you're going to need an exponential number of shots in order to train as your system size grows. Okay. Now, there are many different causes of bound plateaus. The original paper was this one by Jad McLean et al., where he showed that using an inappropriate choice in circuit, namely one that is too deep, leads to bound plateaus. We then sort of, I guess, refined this analysis slightly and drew a connection between expressibility and trainability. So specifically, we showed that, so I said before, you're going to want to use a highly expressive ansatz to maximize the chance that your ansatz contains a solution. In fact, you really, really don't. What we show here is that if your ansatz is highly expressive, then you're basically guaranteed to have a bound plateau. But if your ansatz is inexpressive, you can potentially avoid bound plateaus depending on other features. One of those features is how entangling your ansatz is. So if you use an ansatz that's too entangling, then even if it's inexpressive, you can have bound plateaus. Okay, so those first three were all basically using an inappropriate choice in parameterized quantum circuit. In this paper here, we showed that actually certain target learning problems are untrainable, no matter how good your parameterized quantum circuit is. So specifically here, we show that if you were trying to learn a typical random unitary, or equivalently a typical scrambling unitary, then you're going to unavoidably end up with this bound plateau landscape where you can't learn. And actually, I think we're increasingly aware that this result is symptomatic of a broader problem, that too much randomness in your target problem leads to bound plateaus. And then this was a really fundamental result by Marco Cerezo, So what he showed is that not just your choice in learning problem or your circuit can lead to bound plateaus, but actually your choice in cost function. So specifically, he showed that if you use a cost function that is global, so requires measuring all qubits, then for basically any randomized quantum circuit, you're going to have a bound plateau no matter what, even at very shallow depths. But if you have a local cost function at up to log depth, you can have trainability guarantees, where you're guaranteed at least initially to have some gradients. So yeah, that's sketched here. So if you have a global loss, then your ansatz is inexpressive. Then if you have a global cost, then even very inexpressive low entangling ansatz are also untrainable. So you have these globality-induced BPs at all depths, at least for random circuits. But for local costs, you can have trainability guarantees at log depth. And finally, I know there's a lot of different causes, noise can lead to bound plateaus. So hardware noise flattens out your landscape, making things untrainable. And we sort of historically, I've sort of presented this kind of historical account where we sort of slowly identify these different causes. Recently, Marco's put out this nice paper where it sort of unifies all these different causes into a single story based on sort of group theoretic ideas and dynamical algebras. Okay, cool. So that was expressibility and trainability. I started off saying we wanted to have both expressibility and trainability, but actually we can't have both. So one of them's got to go. And actually it's going to be expressibility that we're going to have to do without, because crucially, you need stuff to be trainable, but actually your ansatz doesn't need to be highly expressive. It just needs to contain a good approximation of your solution to your target unitary or whatever your target problem is. So the solution is really going to be here to try and use problem-inspired ansätze and build symmetries and prior knowledge about your target into your guess unitary. Okay. And one idea for how you could do that is in this sort of this group invariant equivariant framework that has been developed. Okay, so everything I said there, I've sort of framed slightly in the context of quantum process learning, but actually holds more generally for hybrid variational quantum algorithms and multiple quantum machine learning. In the final bit of this talk, I'm going to move on to talking about generalisability, and there I will focus exclusively on this process learning example. Okay. So remember the key question from before. You sort of fiddled around with your guess quantum process. By training on training data, you've come up with this sort of learned quantum process. You then feed in some input state you've not seen before. You get some predicted output state, V of alpha, opt acting on phi. And then the question is, how well does this actually match the true output state? So that is, how well can we use the learned process to predict outputs and unseen inputs? So this question can be answered using generalization bounds, and generalization bounds effectively quantify our prediction performance in terms of our training performance and various quantities about our model. Okay, so what is the prediction error? The prediction error is just the difference between the true output and the guess output. That is the distance between these. And in general, what we're interested in is the average prediction error. So that is the average difference between our true output and our guess output, as averaged over a bunch of states in what we're going to call our testing ensemble. So this P is just going to be the testing ensemble, the ensemble of states that we care about predicting the action of the process over. And note that this average prediction error is often called the risk. Okay, and what we're going to do is we're going to try and relate the prediction error to the training cost. So the training cost, you'll recall from previously, is just the average distance between our true outputs and our guess outputs over the states in our training ensemble. So note here, I'm now using this subscript Q to denote the ensemble of states that our n training states are drawn from. Okay, so generalization bounds quantify the risk, so that is the average prediction error, what we actually care about, in terms of the training cost, the average over the training data, what we actually have access to. And studying generalization bounds for quantum process learning has been a really active area of research over the last maybe 4 years. And in general, sort of the punchline is that conceptual progress has shown that quantum process learning is easier and easier than we originally thought. And I'm going to sort of take you through this story slightly. Yeah, so my focus today will be these two papers, recent papers by me and collaborators, but let me take you through the background and some sort of subsequent results since then. Okay, Right, so this paper here was the one that sort of brought this area of research to my awareness, at least. And what this paper does is it essentially formalizes the intuition that if you're trying to learn a unitary on n qubits, you've got this exponentially large matrix. So you have exponentially many columns and rows. And this paper essentially formalizes the intuition that you're going to need basically a state per column in order to learn each column of that unitary matrix. And then if you've got exponentially many columns, that basically means you're going to need exponentially many states. So there's a sort of simple intuition that you're trying to learn this exponentially large thing. Odds are the amount of training data you're going to need to learn is going to be exponentially large. So that's in that paper. Then what we showed here is actually you don't need exponentially many states if you use a highly entangled state. So specifically, you only need a single choice state. So if you take an input state on n qubits that's entangled with an n qubit register, then you can basically generate the choice state of your quantum process. And if you remember or did this in quantum information theory, you'll know that your choice state associated with a particular quantum process contains all information about that quantum process. So all you then need to do is learn that single choice state, and you've done your learning. So that was the idea in this paper. So it's efficient in terms of training data, but it's not that great on NISQ devices because you need these massive choice states. Okay. So then came along this paper, and this paper showed that so these last two results hold for any unitary, so any unitary process. This paper simplifies the problem slightly, and it applies to efficiently representable unitaries. So efficiently representable unitaries are those can be captured with an ansatz using only a polynomial number of parameters. And they showed that in this case, you don't need exponentially many states or a choice state. Actually, you can only get away with a polynomial number of training states. So actually, the result states that roughly you need the same number of training states as you have trainable parameters in your ansatz. And if it's for efficiently representable unitaries, that's only a polynomial number of trainable parameters. So you only need a polynomial number of training states. But in general, these will need to be basically randomly chosen quantum states, a complete mix of different quantum states. And so actually, these will generally require deep circuits to prepare these training states. It's not that easy. Okay, so this paper here that I'm going to go into a little bit more detail about, we effectively get rid of this deep circuit requirement. So we say you only need a polynomial number of training states, and actually you can get away with some really, really simple training states. Okay, so to spell out that result, I'm going to draw a distinction between what is known as the in-distribution and out-of-distribution generalization. So remember, generalization bound to quantify the risk, what we care about, the average prediction error in terms of the training cost. So the average error of the training data, what we have access to. And this prediction error is over your testing ensemble, and the training error is over your training ensemble. Okay, now in distribution generalization, as maybe the name suggests, is when your training ensemble is equal to your testing ensemble. So whatever training states you're training on, your testing states are going to have to look pretty similar, and vice versa. The question here is really how many training states are required to ensure good generalization. Now, out of distribution generalization is when your training ensemble does not equal your testing ensemble. So in this case, you might try and train on just one type of training data, here sort of sketched as red array packets, but then try and test on a different type of training data. So the question here is not just how many training states do I need, but also what type of training states are required to ensure good generalization. And what our result is in that paper is we showed that quantum process learning is possible via out-of-distribution generalization using only relatively few product states. So specifically, we're going to take our testing ensemble to be the uniform distribution of quantum states. So that is the Haar-random ensemble. So Haar-random ensemble, uniform distribution of states, will typically be highly entangled states. So these are going to require deep circuit prepare, but are sort of a natural choice in the types of states we care about. And then our training ensemble is just going to be random product states. So this is possibly the simplest set of states that we can imagine looking at. So these can be prepared using only a single circuit layer, requiring a single cubic gates to prepare, and can be classically simulated. And then what we show is that this bound holds. So on the left-hand side, we have the expected risk over random states. So that is the average prediction error over the uniform distribution of states, kind of naturally what we care about if we're trying to learn an unknown unitary. Then the first term on our right is going to be our training cost using only n product states. So that is training, assuming we just look at the action of the unitary on n different product states. And then we have this correction term where t is the number of trainable parameters in the ansatz and n is the number of training states. So what we see is that if we have enough product state training states, so roughly n of the order t log t, and then we get the training cost low enough, so that is get this term small 2, then you're guaranteed to have a low prediction error over random states. At least for, and this is going to be a polynomial number of training states, as long as we're working with efficiently representable unitaries where t is also polynomial. So that is, if we have polynomial in n product states as training states and we get the training cost low enough, then this generalization bound says you're guaranteed a low prediction error over random states. So that is, we can learn to predict the action of a quantum process on complex, highly entangled states after only studying its effect on easy to repair unentangled states. Okay, so that was that paper. Now on to this one. And here we switched learning paradigm slightly. So whereas before, all of those results were in this kind of coherent learning paradigm, where effectively, so say this was like some unknown experimental process that you want to learn, and you're trying to learn it on a quantum computer, you need a way of coherently interacting this unknown process with your quantum computer. So before I sort of thought about a trick where you could switch perspectives and think about your quantum computer both as an experimental system and as a quantum computer. That's not going to work if you have I don't know, a superconducting quantum computer, but your experimental process is photonic. In those cases, in this paradigm, this coherent learning paradigm, you'd need hybrid entanglement to be able to link up your experimental quantum system to your quantum computer. So this incoherent learning paradigm is much, much simpler experimentally. Here, you don't need the coherent interaction between your target process and your guess process. These can be implemented on two completely different separate systems. Okay, and then within this new incoherent learning setting, we consider two different variants. We consider the case where you're allowed to perform arbitrary measurements on your quantum process. And then we also consider the case where you're only allowed to do very, very simple, basically single qubit measurements on your quantum process. And what we show is that if you're allowed to do deep measurements, actually in terms of sample complexity, so how many training states you need, this incoherent learning paradigm is pretty flexible and powerful. You can actually learn any efficiently representable unitary in this setting, at least in terms of sample complexity. But this result is practically useless because at the same time, we also have very strong suspicions that our algorithm for doing this in a sample complexity efficient way is computationally inefficient. So I guess unsurprisingly, this incoherent learning paradigm, where you don't need to link up your quantum computer to your experimental platform, is in some sense weaker. We then move to looking at sort of shallow measurements. And in the shallow measurement setting, we find that you can actually learn efficiently representable low entangling unitaries without this incoherent interaction, without the coherent interaction. But for arbitrary unitaries, you're going to need exponentially many measurements. So what this tells us is that you can't learn generic polynomial depth unitaries incoherently, but actually this incoherent learning platform provides a really simple way of learning low entangling unitaries. And actually so simple that we managed to implement a 16-qubit implementation of it on IBM. So here we basically, our algorithm makes use of classical shadows, particularly Pauli shadows, and we managed to successfully learn a short-time trotterization of a 16-qubit transverse field Ising model implemented on IBM-Q's Calcutta device using our sort of shallow measurement incoherent learning algorithm. Okay, so that was that one. And then the final one on the tour, it would be rude of me not to mention this paper. So this paper provides a both computationally and sampling efficient algorithm for learning arbitrary processes. So whereas before, we only had algorithms where we had basically sampling efficiency guarantees, and we only had it for unitaries. In the case of the incoherent learning case, we only had it for low entangling unitaries. This paper bulldozes all of those restrictions, but with a major caveat. It doesn't learn the unitaries in the same sense that I've been talking about learnitaries so far. You're not predicting the correct output states. All you're doing is predicting effectively local measurement outcomes on average. So this is a much weaker learning requirement, and that is how it manages to bulldoze some of the other restrictions we had before. And I think what that highlights is that predicting just certain measurement outcomes is a substantially easier learning task. And you really get that understanding by contrasting these two works. And one thing I want to end by highlighting is that throughout these years, we've actually been in discussions with Alex Marr at the University of Purdue about one day trying to implement one of these learning algorithms on his superconducting qubits. And he's been setting up his lab. And as he's been setting up his lab, we've been essentially making the process of quantum process learning easier and easier. So we initially got in touch with him at this stage and said, right, okay, we want to do this algorithm, but you're going to need to create these large choice states. And he's like, yeah, okay, maybe one day. And then 6 months later, we got back to him saying, okay, no, scrap that. You don't need the choice states, but you do need to prepare like random initial states, polynomial deep circuits. And he's like, okay, that's better, thanks. And then 6 months after that, we said, actually, no, just product states will do. You no longer need the random input states, just do these simple product states, and that should work. And then after that, we're like, actually, you know what? You don't need to do the parameterized unitary on your device. Just do these simple measurements, collect these shadows, we'll do all the post-processing and figure out what process he's got for you. He's a long way off doing this experiment. He's still kind of tuning up his qubits and getting his 2-qubit gate fidelities up. But so I think it's a nice argument that theoretical progress can make the life of an experimentalist easier, because I think we've definitely made his job a lot easier within these last 3 years. Okay, so that takes me, I think, to my final slide. In summary, when I was talking about expressibility and trainability, there was lots of sort of bad news. Well, not really news now. I think much of this is known, but in general, trying to get expressibility and trainability to work out is a major barrier to hybrid variational quantum computing. But in terms of generalizability, actually, there are reasons to be optimistic. Tasks that might superficially appear hard are in some sense easier than maybe you might intuitively expect. Cool. I think that's everything I had to say. Do people have any questions?
Okay, Zoe, thank you so much for such a very nice talk. So now we have time for questions. Maybe I can start. So you mentioned at some point that the average fidelity is straightforward to compute in several platforms. But I thought it was the opposite, that measuring fidelities is hard because the complexity scales exponentially with the system size, right?
What do you mean? Are you talking about mixed state fidelity or pure state fidelity? So I'm just talking about pure state fidelity, and I'm talking about the circuit required to measure it. So what you might be highlighting is that, so it's a simple circuit. The complexity of the circuit is simple. There is the problem that actually fidelity between two states in an exponentially large Hilbert space is likely to be very small, and so you might need many shots. If that's the point you're highlighting, good catch. What you actually want to do is a local variant of the fidelity. So what you do is basically, instead of doing an all zero projected measurement at the end, you do zero projected measurement on each pair of the qubits, on the individual qubits, and then add it up. I might have some bonus slides on this somewhere. No, I don't. No, so I don't have a slide on this, but yeah, the idea is you can switch out a global projected measurement for a sum of local projected measurements, and then you no longer have this problem.
Okay, cool. So you have to rely on a local variance.
Yes, exactly.
Okay. Also, since well, fidelity is actually a global cost function, right? So I mean, if you are trying to learn some quantum process on some unitary, and you use a fidelity as a cost function, you may have these barren plateaus, right?
This is exactly the point that I'm trying to make. Let me get the slides on this. Maybe this. Yes. Oh no. Damn it. Sorry, 1 second. Just press the wrong button. Okay. So what you want to do is, this is what I was just trying to explain a second ago. So if you've got a global cost, so say you've got some global projector here, you can switch instead to using this local cost. So local cost is a sum. So instead of having this global projector, you just do a sum of the projectors on each qubit. So instead of just computing this, you basically sum together the results of these two circuits. And in fact, you actually only need to do one circuit. So it's at the level of post-processing. You don't need to rerun the circuit. You can measure them both, but then do the addition at the level of post-processing so that you're measuring this rather than this. And okay, so this gives you an intuition as to why you have global BPs. So think about this simple problem here, where it's a compilation problem. So you've got a tensor product initial state, tensor product target unitary, tensor product ansatz, and you're working with this global cost. So this is the fidelity cost that I was highlighting. Now, if you compute this, this is just going to scale as 1 minus r to the n, where r is a single overlap term on a single qubit. And then if you switch to this local version, you're no longer basically multiplying each of the bits. So you no longer get this r to the n, but you're now adding them. So you get this just an r term.
Okay.
I think actually if you have this normalization factor here, then you shouldn't have this n here. Okay, so that's why this works. And then crucially, and I don't have the proof for it here, see Appendix C of this paper, you can show that this local version of the loss is faithful to the global version. So that is, if you take a loss of this form and you substitute out this global measurement for this local measurement in the way I've just shown you, then what you have is that the global loss is always less than or equal to n times the local loss. So that means if your local loss goes to 0, your global loss is also guaranteed to be 0. So when I say you use this fidelity cost, it was a slight sleight of hand. You actually want to use this local version of the fidelity loss.
Okay, that's a very beautiful way to show it. Thank you very much, Zoe. So do we have any more questions? Yeah, Jan?
Yes, can I? Sorry, I'm a bit ill. On that topic, so is that just on the very slide? Is that your intuition? So this seems familiar in the context of DMRG, right? Where you also optimize locally state and then get the global state correct as well. So is your intuition something similar or not?
So
do you understand what I'm saying? So I don't know if you're familiar with the DMRG algorithm, but you project out these local degrees of freedom and optimize them in the context of now it's energy, it's not fidelity. But yeah, I don't know.
It's quite different here, I think. You're not just, it's certainly not how the proof goes. The way the proof of this bound goes is effectively like a union bound argument. You're comparing the probability of basically getting all of these, that and that and that, versus that or that. And it's a union bound that basically gives you this factor of n out the front.
Yeah.
And it very much only holds for costs of this form. Even when you've just got a sum of different costs of this form, things break down. So it's quite a sort of fragile result based on the mathematical structure of this problem, rather than a fundamental insight about the nature of the quantum states here.
Yeah, thank you.
Okay, guys, someone else wants to ask something?
I had another question. I didn't catch this, I'm sorry. On your inequality of risk versus cost plus correction, there was this T log T.
Wait. Which this 1 second. Let me go.
Yes. Yes, this slide, yes. I didn't catch, so the definition of the risk function, or sorry, which observables are supposed to be bounded by this, or are they I don't know, fidelities or?
So it's this. So
Okay.
so the average prediction error is the
Mm-hmm.
average distance between your true output states and your guess output states averaged over the states in your testing ensemble.
Okay, so it's a restriction in Hilbert space.
In what sense?
Oh, so this is a norm in Hilbert space, right?
So this is the one norm squared. So this is equivalent to the average. So it's the average fidelity between the true output and your guess output state, averaged over
Okay. Yeah.
uniform distribution of states.
Yeah. No, I just didn't catch this, that it was the fidelity.
Yeah. So it's equivalent to the Hilbert-Schmidt inner product.
Mm-hmm.
Up to some sort of d over d plus 1, some small factor.
Okay. Any more questions?
Yes, I had one.
Okay, Christian,
Okay, so
go on.
thank you for the nice seminar, Zoe. And I was wondering if you have an intuition of how these trainability issues, the barren plateaus and so on, get modified when you consider natural gradients instead of regular ones.
I don't think it really changes much of the fundamentals. So if you have a bound plateau, you're going to have a bound plateau whether you're using natural gradient or whether you're using standard gradient-based methods. But as I understand it, people who are working in those areas show that basically when you don't have a bound plateau, you converge quicker using natural gradient. So I think it's a slightly perpendicular issue.
Okay, thanks.
Okay, so if there are no more questions, let's thank Zoe again. I will end the recording.